commercial system, as we know, is the safest transportation system in the world, and the accident rate is the lowest that it's ever been. This impressive record is due to many factors, including the aircraft design, aircraft reliability, the automated systems, the pilots, the pilot training, the air traffic control procedures, and numerous safety enhancements over the years. The role of the pilot has changed over the years and will continue to evolve as next gen is implemented. Pilots are required now to be systems managers in this complex operational air traffic system that we have, while still maintaining their airmanship skills that we've had to have from the beginning. And pilots also mitigate operational risk in all areas in which they are involved. In fact, our aviation system relies on this mitigation. We complete thousands of flights daily, effectively, efficiently, and get our passengers safely where they need to be based on the contribution of our professional pilots and everybody else in this complex system. In the future, automation is going to continue to play a role as we evolve towards next gen. To enable this new automation systems to function with increased utilization and control, automation is evolving and our pilot tasks, as I mentioned, are going to change. This will place new demands on a system that is already under pressure. This new automation components are themselves a potential new source of error and risk. This is especially true if the automated system implementation and design does not use human factors principles during the design phase. While the ultimate responsibility of flying the airplane remains with the pilots, we have learned that crews are not all adequately trained to handle these automated systems, especially in high-demand situations. Most operators recognize that the use of automated systems may not always reduce the workload, but in fact may actually increase it and lead to error. And when an automated system fails, it's relied on the human pilot to intercede and resolve the issues. It is therefore essential that the pilots are always kept in the loop and clear human factors guidelines are used during the development. And to paraphrase the director of the NASA Aviation program, Amy Pritchett, automation cannot handle the complexities of the next generation air transportation system without humans at the center as integral components and still maintain our current level of safety. Advances in technology and automated systems must be viewed in the context of a systems approach, as I mentioned earlier, where the human is at the center of that system. The most effective automation design places appropriate emphasis on human capabilities as well as their limitations. Automation needs to allow the pilots the chance to handle short-term and short-notice changes necessary to accommodate the factors that underlie, such as weather, when the weather changes, air traffic control routes us off, or just degraded performance or even partial system failures. We still must be able to take control of the aircraft and land it safely on the ground. The automated systems must be clear to the message and the information they provide to the pilots. The pilots need to know the status of the aircraft at all times and be able to predict what the system is doing so they can anticipate changes that need to be made. Today's panel of experts will discuss this development of increased use of automation in today's airplanes, and we're going to look at the last 25 years, including some of the lessons learned. They will discuss where the automation is today and how it will affect us in next gen. To begin the panel, I'm going to have two of our manufacturers who will provide their perspective on how automated systems have affected their design and what they envision for the future. Following them will be Dr. Woods, who will discuss the complexity and new techniques to monitor this aviation system that we call it and the brittleness of that, and look at the overall system resilience. And our session will conclude with the pilot perspective from Dr. Reidemar, providing a pilot's perspective on the operational philosophies and policies of automation. So I'd like to introduce the panel right now. So speaking first will be Captain Mike Carriker, to my left, who is the chief pilot for new airplane development for Boeing. Next to him is Captain Terry Lutz, who is the experimental test pilot for Airbus. and former ALPA member. Dr. David Woods, next to Terry, is the professor at The Ohio State University. And at the end is Dr. Helena Reidemar, our Director of Human Factors for ALPA. So Mike, it's your craft.
Thanks, Dave. The last time I stood on the stage at the ALPA Safety Convention was 2002. It's fascinating to think of the differences between the concepts of the presentations in that day and the presentations you listened to for the last couple of days. I don't think anybody in 2002 worried about cargo security at an ALPA Safety Convention. It's interesting times. So as Dave says, where are we going? Sometimes you have to know where you're going because where have you been? It's an interesting concept. It's very difficult in this day and age with so many players involved in all these conversations. Terry and I were just discussing airplane capabilities where the airplane is not the limiting factor, nor is the flight crew, but the infrastructure that holds it is maybe the limiting factor. How many flew in 1970? Yeah, maybe FEs on a 27 if you're still flying today. So what were the most often questions asked in 1970 in the flight deck? Okay, what's the outbound? Okay, how many of you folks are not are still flying slant alpha airplanes today? Yeah, I do. The airplane I fly tomorrow is a non-RNP capable airplane, so I have to follow all these waypoints. What's the inbound? The other question. Was that for us? All right. You know, my God, what airplane are we flying today? What's the call sign? At Boeing, we only fly under about 5 call signs. And if I don't hear the word Boeing, if I'm flying somebody else's airplane, I don't hear the word Boeing. It doesn't compute in my head. And can I get a cup of coffee? Okay. So what are the questions most often 2012? How do you spell that fix? We just took the 787 to the Farnborough Air Show, and you know, we got cleared to this fix and that fix. And we were madly searching the Jepson, and finally we just asked, you know, the British controller, can you just spell that for me, because I can't figure it out. Was that for us? So we must not have made too much improvements in there. You get the flight attendant up here so I can use the lav. Nobody thought we'd ever have to call up another person to sit in the flight deck to use the lavatory, right, and secure the lavatory. And can I get a cup of coffee? So why did these questions change? What in the history of aviation in the last 25 years, what has stood the test of time? What haven't we changed, all right? What have we added to flight operations? Well, we've added obviously lots of things. Why did we add it? That's always a question. Why did we add it? Is that a precursor? Is that a flight data recorder data read that says why we do it in the French? Did we subtract anything? Yeah, I think we subtracted something. I think we subtracted a thing in basic pilot skills. This Saturday, I should go for my B-25 type rating, right? And that airplane, it takes 5 fingers to start the engines. So, and you know, but we don't want to have to, anybody has to watch the color of the flame to adjust the mixture of an engine anymore. That's not a very good idea. Very interesting question. Can we track efficiencies versus complexities? We can always make things more complex, but would we actually make it any more efficient? Are we better? Are we better? When Alan was the president of the Boeing company, he had a meeting with us. This is the original 20 people that made the 787 program. We're sitting around this meeting in his office, and he said, your mission to the team there is to make a safe and efficient global air transportation system. Be a key participant in a safe and efficient global air transportation system. Our collective mission from the designers to the controllers to the security people, the maintenance people, to the people that operate the airplane, has never changed. It is absolutely unequivocally about safety. If we ever lose the safety of the theory that we not have a safe flight, we're all out of business. Nobody will get on our jets, no matter how wonderful the coffee service is or the TSA is. And as Dave said it very eloquently, better than I can say, we're actually very, very good at it. I ran through the statistics of the predictions in 1990, and we are bettering the requirements of the safety event analysis of 1990 as the rates, of course, as the rates of flights go up. So we're actually better than what we hope to do, right? But we know we have to keep going better because the future is out there. When Dave asked me, you know, when you want to come talk about this, this was the first set of impressions I had. And he says, why don't you talk about the future of aviation and technology and what are you going to do? And I drew a big blank. Right? But I kept thinking, airplane changes in the last 40 years. So anybody got 727 time? Yeah, maybe probably as FEs if you're still around anymore. So the 737 autopilot, autoflight had a heading hold, altitude hold, and VOR track. That was all it had. Flight director wasn't coupled to the autopilot. No auto throttle system, no manually tune all the frequencies, distributed caution and warning systems in the overhead panel, manual systems control, and then for your oral, you could legitimately draw the system on the chalkboard. Okay, the 7878, 777-300, auto-flight guidance, you hit on the 787, from hitting the toga button on the takeoff roll to coming to stop at the end of the runway, we will provide you left-right guidance. Once you get airborne, we'll provide you up-down guidance. We'll provide you indication of deviation from the path, and we'll provide you for warning of excessive deviation from the toga push until the end of the rollout. Obviously, the flight director is integrated with the auto flight system. Auto throttle is full-time auto throttle. FMC tunes the navigation system if it has to. GPS gives you accuracy the unbelievable 15 years ago. The ring laser gyros and the AHAR systems we use in the airplane now to use differential GPS arrival at the airplane to sweeten the answer. We have FADEX, right? Auto start on the engines. Auto start on the engines are there to protect the engine, not to ease the pilot workload. Auto relight. Technically, in the 787, if both engines fail, it's not in your procedure because it's different than a 777. In a 787, if both engines fail, you hit filch, heading select, and sit there because the autopilot stays engaged on the rat and the engine's going to auto relight. Closed loop flight control systems with alleviations and compensations, my favorite part of it. ICAS systems, automated systems controls, and if you ever looked in the inside of a 78 or a 777 and you think you drew on your oral that was really in the airplane, you're dreaming. You're flat dreaming. And it goes into the concept that Dave spoke a little bit earlier about, and that's the fact that we are systems. The airplane, the whole thing is a system. The people and the pilot and the airplane makes a system. Why do we change? Why do we change? Safety. Right? Cost to operate, cost to build, meet regulatory requirements like the next gen. The customer wants it. There's probably 4 more in there, and then the last one, this is one I have to deal with all the time. The pilots think it's really cool. Okay? So all those people that want their iPad holders installed on the yoke, skip it. We have embedded infrastructure. We have 5,000 737s in service, just the numbers. 15 pilots per airplane, $30,000 estimated cost for training. Do some public math. $2.25 billion in capital invested into flight crews around the world. At Farnborough, Boeing said that we think the airline service is going to require 460,000 more pilots in the next 20 years. As far as I can figure out, that exceeds the capacity of the training system today. So unless you know of a really killer application, the competitive race for us right now is to get 787s out the door, get 777s out the door, get the 737 MAX out the door, and get it into our customers' hands. Thanks. Oh, there was one other thing. This is the most game-changing piece of equipment in the flight deck. The applications written for this and the ability to get what we call 121 information published on this is going to rapidly change the way we get information in and out of the flight deck. And it really will make, if you put a good receiver on the airplane, it really will bring all airplanes in worldwide service as being a node on the net. And that will be one of the fundamental changes that we'll have to deal with in the flight deck. Thanks.
And thank you, Mike, for that wonderful perspective. And we agree is that the information management that we are all dealing with today is almost an overload of information in the flight deck, and we're going to have to figure out how to use that and what to use and what not to use. So next, I'd like to introduce Terry and let him come up and give the Airbus perspective on how he thinks automation. Thank you.
Good morning, everyone. It's a pleasure for me to be here. It's a pleasure for me to be able to give back something to this industry that helped me so much in my flying career and helped elevate me to the place where I am now at Airbus as an experimental test pilot. What I'd like to talk about a little bit today is integrating technology with piloting to give a slightly different perspective than Mike presented, but you'll see some similarities along the way as well. If you look at airline operations in 1965, it was really the end of the reciprocating engine aircraft era. There were still some DC-6/7 airplanes in service as well as the Super Constellation. The 707, 727, and DC-8 were the first jet engine aircraft. They were in service. 737 and DC-9 soon to follow, and later the 747 in 1970. At that time, there were no computers, no satellites, no INS approaches, and all navigation was mainly flown with VOR and ADF. Few precision approaches, and for long-range operations, poor communications coverage and poor weather information on a global basis. The role of the pilot in 1965, aviate, navigate, and communicate with the help of a flight engineer to manage the systems. The flying task was essentially an extensive manual skill set, and the mental skill set required was focused mainly on instrument flying. It required of the pilot a solid knowledge of the atmosphere and weather, basic aerodynamics, and airfield capability. And when I say airfield capability, what I'm discussing there is on a given runway, at a given weight, can I get off this runway with the required performance both from a climb standpoint and an accelerate stop standpoint? And if you put that in the landing case, can I land on that runway given the weather conditions, the runway condition, the runway length, where I want to turn off, etc. So those basic required skill sets, knowledge of the atmosphere and weather, basic aerodynamics, and airfield capability are what the pilot really needed to know in 1965. Let's have a look today and see what skills are required. Airline operations in 2012. The A320 and the 777 were the first fly-by-wire airplanes, and they've been in service now for almost 20 years. Almost all the airplanes flying today have glass cockpits with LCD displays, and routine overwater operations are conducted now with twin-engine airplanes. We're beginning to see, and of course with the introduction of the 787 and later the A350, primary structural elements are being made of carbon fiber to save weight and increase performance. Computers, lots of computers. We have GPS with GBAS and WAS for augmentation, triple IRS, FMGC to integrate everything so you can have extremely accurate navigation. With augmented GPS, we can fly approaches to almost any airport that's long enough, with a runway long enough to Cat 1 minimums. For communications, one of the things that was lacking in those early days, you couldn't communicate on a long-range basis, but now the VHF has a data mode, HF has a data mode, and SATCOM has a data mode. So with SATCOM, CPDLC, you have tremendous long-range communications. And in addition to that, we have a lot of weather products that are produced by satellites. The airplanes themselves can report the weather conditions back to the ground stations. So you have excellent global weather capability today. The pilot's role, how has it changed? It used to be aviate, navigate, communicate. The navigation and communication roles are now largely automated, but the pilot still has to do the basic aviating task. And a new task has been required of the pilot, and that's to manage the overall mission. Systems today have been largely automated, and those of you who wrenched on the 727 know, and you had a manual pressurization system, you're very, very thankful that modern airplanes have automated pressurization systems. But the managed mission means is that the pilot now he has to really consider everything going on with his particular flight in terms of once you're airborne, let the airplane do the navigations and a portion of the communications, but what you want to do is manage that flight to get it to the exact position that you want, either in space, on the approach, for example, or on the runway at a specific time for your company so the airplane can get to the gate, turn around, a new load of passengers, and be on to its next destination. If you look at the flying task in 2012, you realize that there is still a manual skill set required. But there is now a new skill set which is extensively mental that's also required. But what remains unchanged? The atmosphere and the weather haven't changed, basic aerodynamics haven't changed, and airfield capabilities in terms of what you can do with that airplane on that runway has not changed. I want to give you two examples about how technology has changed the pilot interface. And those examples are what's happening with flight controls and what's happening with engine controls. If you look at the Boeing 727 autopilot controller, which is probably the best manual autopilot controller that I've ever flown, there were two axes in one controller. It fit your hand very, very nicely. It was located just behind the thrust levers, so you just had to move your hand over and use the autopilot to control the airplane. It had excellent HMI, force, displacement, and rate capability. In pitch, what you had is a pitch rate command, pitch attitude hold, and in roll, what you had was roll rate command and bank angle hold. If you go and look at today's controllers in fly-by-wire airplane, whether it be the side stick controller that we use in our airplane or the manual controller in the Boeing 787, you also have two axes in one controller. Excellent HMI for force, displacement, and rate capability. And in pitch, you find that it's basically a pitch rate command, pitch attitude hold, and in roll, a roll rate command and a bank angle hold. So you can view the controllers in modern fly-by-wire airplanes as either super autopilot controllers, or you can view them as pilot controllers where the airplane itself is compensating for all of the undesirable motions for the Dutch roll, for example, for the short period mode of motion, for phugoid, and to control the spiral, which will allow you to fly a very, very precise bank angle. What about the engine controls that we have in today's airplanes? This is a picture of a hydromechanical engine control. I actually had difficulty finding one on the internet. This is from a Garrett TPE 331 turbopropeller engine. It's a highly optimized mechanical control, but it's very complex with a high parts count. Difficult to maintain, expensive to overhaul, has a very long mechanical mechanism from the cockpit out to the engine. And even when it's rigged to the best of the mechanics' abilities, there was usually a thrust lever split that you had to compensate for when you were flying the airplane. One last thing that's not on this slide is with the hydromechanical fuel control, you probably didn't have over temperature protection for the engine itself. Now let's look at today's FADEC. You have excellent engine control without exceeding engine limits. You have an optimized controller that will actually extend the engine life, which is near and dear to the pilot, to make sure that those engines are going to run and run for a very long time. It has an internal power generating capability within the engine itself, where there's a small alternator that will power just the FADEC in case the engine loses total electrical power from its normal generator source or from the airplane itself. But I think what's the key is that there is no longer any direct mechanical linkage, so that you can have perfectly matched thrust levers, and you might call it a thrust-by-wire system. So when you think about these technology changes and how they've affected the pilot, you may not have ever thought about it that way, but as technology changes the pilot's role in how he interfaces with the airplane, is the traditional knowledge base of the pilot being overlooked? What about the weather? What about basic aerodynamics? What about the runway environment? Are we overlooking all of those that knowledge set that the pilot needs in the process of improving technology in the pilot's role? Is the training environment adapting to technology integration and focusing on that extensive mental skill set that the pilot needs in today's airline operation? And finally, as a thought provoker, are mandatory training requirements outdated considering the technology improvements and the changing nature of piloting? We can have an airplane today where you can take off at maximum gross weight, have an engine failure, and continue to rotate and take off, and the airplane will stay wings level, maintain its heading, allow you to climb out and operate your normal procedures after that. It's not the same as the airplanes that we flew in 1965. Does training need to adapt to those new technology improvements? Thank you.
Thank you, Terry, for a wonderful perspective. So as we see the aircraft are changing, the pilots' roles are changing, the way we do training is changing, and it puts a lot of pressure on the system, as I mentioned earlier, that's already under pressure. and we have a lot of new pilots that are going to be entering our workforce, as Mike said, in the next 20 to 30 years. So to speak about the resilience of our aviation system, I'd like to now introduce Dr. David Woods.
Wow. I mean, you just heard, right? Reflect on what they just talked about for a second. It's very complex what you do. It's extremely complex what you manage. You have to do it under fast-paced conditions. Sudden things can happen, unexpected and non-routine events occur, right? This is the sea of complexity that you operate in. And you are, despite all the other good things they talked about, you end up being a critical ingredient in making this complexity work every day. And other people in a wide variety of roles, right? ALPA, the vendors, the flight safety groups, all of these people in these different roles in the total aviation system keep adapting and learning to make it work. But as our great American philosopher Yogi Berra said, right, even if the world were perfect, it wouldn't be. How do we perform better when we're under constant pressure, right, to be faster and cheaper and improve each individual part of the total system? These seas of complexity are not just yours. In fact, in many ways, you're leading and teaching others about how to navigate these seas. We see this in operating rooms. We see this in space operations. We've seen this in military command and control. Now, the opportunity here is there's new advances in science. The complexity sciences study how adaptive systems work, how people in various roles learn, recognize, anticipate. In our world, we talk about it as proactive safety. But there are new findings, new concepts, new laws, all right, about how human systems adapt in the face of complexity. Now, intellectually, this is very non-intuitive. You're used to simplifications to make things work. You focus on one piece at a time. They focus on one issue at a time. Then they try to make the interactions work. From a complexity point of view, the system is all in the interactions and what emerges. It's all about more and more extensive interdependencies. Now notice how the automation creates a layer of apparent simplicity over those increasing interdependent relationships between more and more parts, so that everything looks simple and runs super smooth until it doesn't, just like Yogi Berra reminded us. And then we see cascades you have to try to keep up with. We see tipping points. We see surprises. We have to integrate across multiple perspectives, and we have to not simply find a good operating point, but we have to be able to maneuver as organizations, as learning organizations, in the same way that you have to control the capability for maneuver in the aircraft. In the face of this, the critical concept is when systems fail, they reveal points of brittleness, and they reveal hidden sources of resilience. People are often the hidden source of resilience in one or another role. Sometimes we restrict the ability of people to act as a source of resilience in one role, and we need to make up for that in other places. The question is, can resilience be engineered into organizations that carry out complex activities? Can we measure and monitor for increasing brittleness and act proactively, especially as we're making changes to be faster, better, cheaper? Well, for me, resilience started with NASA's history. We just had a great landing on Mars, but you may remember in 1999 we had 3 failures. And NASA started a project called Design for Safety. The diagnosis from the 2000 accident report was increasingly brittle systems under faster, better, cheaper pressure. Now, a variety of things happened, and then we had a repeat in the Columbia accident where I was able to be an advisor to the investigation board. This is a slightly edited for visibility slide from 2000. And I want you to think about, right, and remember what we just covered, right, and how it applies to you today. NASA exists in a changing environment with new performance demands and resource pressures, driving down costs, shorter, more aggressive schedules, new partners and relationships, new roles, skill erosion, heightened public interest. The question they posed was what could be a new dimension that could be used in management as important as cost and schedule. And the proposal I made in 2000 and in the aftermath of the Columbia accident here in DC to NASA and to Congress is that resilience, and that we have started this development of resilience engineering. Interdependency is complexity. We just got hints of it in the demonstrations they gave us. I normally run through some fun examples of these interdependencies and how they produce unintended consequences. This is counterinsurgency diagram that came out a year or two ago, right? A great spaghetti map of all of the interdependencies they have to work through in terms of managing these kinds of operations overseas. So operating in seas of complexity, while intellectually non-intuitive, you experience how to do it every day. As a key adaptive element, a source of resilience in the aviation system, you have to deal with hidden and dynamic interdependencies. You have to handle challenges when non-routine and unexpected conditions arise. You have to be able to keep up with a cascade of events. When a sensor failure cascades and you don't know what to trust in terms of cockpit indications. What we're trying to do is understand and measure how systems are brittle and how we can bring extra adaptive capacity to bear. And the concept is actually from you that we're using to teach other people about how to do this. And we can take the concrete example of you and flight control systems and say, in order to maintain, to be in control for the future, for the next event that might occur, you have to maintain a margin of maneuver. You have to maintain a control margin that you can act to compensate for those unexpected or non-routine events. Now, what we see over time is cumulative, creeping, inadvertent complexity. The unintended consequences are increasingly brittle systems, so that our failures are not due to a component or even several components failing, as is still typical in how we try to learn from incidents, trying to improve individual pieces of the system. As a complex adaptive system, we have to see it's in the interactions, and therefore how the incident or accident tells us about brittleness and sources of resilience. Otherwise, we will continue to see surprising failures and continue to play whack-an-incident in trying to react and keep up when our intent is to be proactive. Now, there are regularities about how complex adaptive systems fail. We don't have time to run through them right now, but you are well prepared to deal with these most of the time because of your skills, all right, as effective pilots. Right? When we think about resilience and brittleness, the best thing is to think of images you encounter, whether it's a UAV accident, whether it's a friendly fire incident with the Patriot missile, or whether it's more humorous cases where the introduction of GPS in England has led to new signage warning people not to follow their satellite navigation because large trucks, lorries, tend not to be able to go through small lanes in English villages. We just finished this week, and I believe it's being released, if not today, in the next couple days, a report on autonomy for the DoD as a part of the Defense Science Board. In this report, we run through many of the different issues in how to deal with resilience and brittleness, and that the major shortfall that undermines the potential benefits of more autonomous, more automation in our systems is the inability to take a true systems perspective. We focus too much on individual platform capabilities, subsystem capabilities. And what we need to do is look at it as an integrated system of people and computers managing potentially escalating and cascading situations. And what's also interesting in the report is how we point out that you don't have to be pessimistic in the face of complexity. There are ways we can anticipate, just like you anticipate problems and prepare for them as you run safe flights. You do that in terms of alternate destinations, understanding fuel margins, understanding small changes, right, that require your vigilance in the situation. In the same way that as a larger system, we can anticipate bottlenecks ahead. We can look for unintended consequences. Complexity science and resilience engineering are building new ways to do this, including new measures to assess how brittle the system is part of introducing new technology. So what's the simple summary of a complex adaptive system resilience approach? You've gotten good because you've adapted. People in a variety of roles have anticipated and learned, sometimes through bitter experience. The difference is when you look at those cases, or when you analyze new cases, we need to start seeing them as stories that reveal brittleness and hidden sources of resilience. When we comment on de-skilling of pilots, we are addressing a loss of a traditional source of resilience. Right? When we have new ways that a single small failure propagates and influences multiple systems because of the interdependency created by multiple automated subsystems, right? We're increasing the challenges, right? Increasing the potential for cascade, increasing the difficulty of responding effectively under time pressure. When we look at today, despite the success, not just despite the success, but because we are so successful in balancing efficiency and safety, we actually, again, the Yogi Berraism captures it for us. Even as we get better, the fundamental system trade-offs that was on that slide from the Defense Science Board report indicates that we introduce new points of brittleness, new complexities people have to deal with. The present is more precarious than we think. And it's a common finding from all approaches to safety from an organizational perspective that safe organizations are constantly on edge, recognizing that past success is no guarantee of future ultra-high safety performance. How do we create a resilient future requires new partnerships, integrating multiple perspectives at different levels and echelons across the industry. It deals with future cases, whether it's next gen, whether it's introducing remotely piloted vehicles into the domestic airspace, whether it's dealing with new ways to improve cockpit information. Right? Creating a resilient future is going to require new working relationships and new partnerships. We have techniques and we have measures that are rapidly emerging, and we're looking for new partners in terms of testing, right, and developing practical. That's why we called it resilience engineering, to be that we can translate the science into practical things organizations can use. Right? And the fundamental thing we point to is we take the example that you need to maintain a margin of maneuver in terms of control systems, whether automated, human, right, or a combination, and that concept generalizes and actually fits into some of the theoretical development so that we can actually build resilient control systems, building on the history of success in other kinds of control engineering domains. So we're working with Idaho National Lab, for example, to actually develop the basic technical findings in order to create new kinds of resilient control systems, which ironically will be both, right, highly computational, highly computerized, and highly human in these systems. Can we escape complexity? Can we escape it by simply reducing and simplifying? No. But we can outmaneuver complexity. Right? That's the necessary future to maintain the success we've had in the past. Thank you.
Wow. So as you can see that the complex systems that we deal with today, and we can only anticipate what's going to be coming in the future at us, if we maintain the status quo, we're not going to be able to maintain the safe record that we have today. The pilot is only one component of this system that we've been talking about. And as you can see with the complexity, a lot of times what we deal a lot in this room is the pilots, their training, and how do we react to the surprise when something fails. A lot of our job, nothing happens during the flight. So we have to figure out how do we change this, how do we become the systems managers, and how do we work with other people. So based on what we've heard already, I'd like to have Dr. Reidemar come up, and she's going to talk to us about how we take some of the automation philosophy, how do we develop these philosophy and procedures that the pilots deal with in our everyday flights.
Good morning. Before I jump right in, I want to actually make mention of the fact that about 14 years ago, I was a first officer for Captain Lutz over here on the DC-9, And in that one-day trip, or no, it was a 5-day trip, but in that one trip, I learned more about performance engineering than I think I have since. So thank you. And it's great to have you here. I'm going to take a little bit of a step back from the specifics of what we're talking about and maybe look at the process part of developing automation policies, automation design, the flight path management. So a little bit more of a high altitude perspective. We're standing at the threshold of next gen. And it's important not to jump right in and dream up new inventive methodologies for automation policy without reflecting on where we come from an operational and philosophical perspective. We need to look at the evolution of our industry and how this should shape our trajectory going forward. We're very quick as a group, as an industry, to be problem solvers and say, hey, this is the best way to operate this piece of equipment. But we need to take a step back and consider the overall organizational philosophy as well as the science. And new emerging flight path management policy has to be part of an elegant whole for proficiency, standardization, coherency, in the broadest sense. And it all starts with a well-articulated company philosophy, initially developed by the earliest business plan by the founders, and it includes everything from the essential culture of the company to the conceptual engine that propels the organization forward. And this is also where you'll find the vision and direction for how the company is to be operated. So policies guide the operation by translating the philosophy into an operational context. It establishes the organization's policy of prioritizing the mission of the airline. And every airline has a different mission philosophy. Let's skip through that. So here's some of my thoughts for effective automation policy. And we need to be more explicit than we have been. And traditionally, we've seen a lot well, over the past 20 years, use the maximum automation available as necessary for your phase of flight. That's no longer sufficient. So here are some of my thoughts, and these are excerpts from a paper I'm working on with a colleague of mine. So the operator has to be knowledgeable, considerate, and highly sensitive to the limitations of the automation. Also minimize the impact of flow on the flow of traffic, and then maximize the smoothness and elegance of the human automation interaction, mode switching, and crew interface. And I believe both Mike and Dave sort of hit on some of these high points as well. So moving forward, to maintain a linear and consistent process, policies direct the development of procedures, and this provides for overall internal coherency, and as such, it provides a method for executing the prescribed tasks, and this group knows all about procedures. So, looking at the 4 Ps framework, Dr. Asaf Dagani provided that for some guiding principles. In flow diagram form, this is what it looks like. Philosophy dictates policies. Policies are translated into procedures. And then at the very bottom, we have practices, where the rubber meets the road. And realistically, we can write the best philosophy and policies and procedures, but how does it hold up in reality? And that's the true test of reality. And we see that in our work all the time. So, last of the 4 Ps is practices, and it's what we do every day. It's every activity we perform on the flight deck, and ideally should conform to procedures and policies. So here's a circle model to display the relationships visually. In a perfect world, philosophy would be the overarching guidance for policy, which dictates procedures and then results in practices. Sometimes there's no established procedure for a situation, but as long as you have policy guidance, however, the expectation is very clear. You may even find a situation where there's no policy guidance, but as long as there's a clearly defined philosophy and an articulated philosophy, the pilot has a general understanding of expectations. Unfortunately, we can find ourselves in situations where there is no overarching philosophy. And this is truly problematic for the pilot and the organization. Now you're in uncharted territory. Nobody wants to be there. And it's not expected in normal operations. Perhaps the aircraft is doing something unexpected that we have no mental model for. Think Air France 447 or Colgan 3407. The complexity of component interactions can truly lead to some unanticipated systems behavior, as Dr. Woods was just saying as well. I had some thoughts for, some other examples of the same kind of thing. All right, so the 4 Ps framework. So here's the ideal. Philosophy is the guiding light. From that emerges culture and policies for everything, automation, emergencies, abnormals. And then this translates to procedures, checklists, flows. And both policies and procedures are based in science. This is the ideal, of course. And then we have the actual behavior during line operations. All right, that's not real pretty, right? 4 Ps framework, maybe more realistic, rumor has it. So philosophy is sort of hovering off in the distance and loosely directing policy, and scientific principles off to the side, and a random feedback mechanism. Not exactly SMS ideal. In any case, procedures and policies were written and designed, they were tested in the sim, but how did it hold up in practice? And how did it correspond to reality? That's the essential feedback loop, and we need that. We know procedures are never 100% perfect, but it's important to get the feedback to do the modifications. So what can we do? With respect to automation. First and foremost, consider the manufacturer's policies and philosophies of automation. They have a design philosophy, and that needs to be where we start. And then we need to work within our own organizations to fix the disconnects. Heading into next gen, that's more important than ever. Only after we look at their philosophy and our own philosophy can we move towards specific policy and flight path management. Just some looks at different philosophies of our manufacturers. And it's very important to know the environment you're working in and to start with that. That should be the foundation. I know, a little bit of an eye chart. I wanted to expand on some of the parts of it. And I know Boeing has evolved a bit with the 787 from that, and we thank them for it. So, the airlines need a much more salient automation philosophy or flight path management policy. Manufacturers' automation philosophy is about design, and it doesn't talk about the operation, and it provides little guidance for training, procedures, division of labor, workload management. And many of us operate both Airbus and Boeing on property, and others as well. So really important to go back to the foundation before we jump in to create new procedures. I got a couple of examples just to kind of illustrate some of my points. So Airline A, if you want to read it, there's the philosophy. Basically, this is how they operated for 30 years. Their philosophy and procedural automation guidance, pretty clear, don't do it. So then they realized potential savings in both time and fuel in using automation effectively, and the whole airline policy had to be rewritten. It wasn't just about rewriting some procedures. It was an entire shift, paradigm shift in their philosophy and their culture. It was a significant change. So be cautious in just changing the order or flow of things. You need to actually back it up and support it with policy so the expectations for the pilot is clear. Another example, and the specific point here is, well, we have Airline B and some aspects of their philosophy, and their more rigid culture required open descent restricted below 1,000 feet on the A330, directly related to their culture, because then we have Airline C, much more flexible culture, and they only restrict their open descent at 500 feet on the A330. So two airlines operating the same aircraft with significantly different philosophical differences in their automation policy. All right, so back to this slide, elements of style for designing an automation policy, or a flight path management policy. The biggest emphasis I feel the need to make at this point is the necessity of increased, more appropriate, customized training for the pilots in the automation that we're expected to operate. In the near-term future, we'll be working with tighter tolerances, self-separation, 4D trajectory. We need to maintain manual flying skills more than anything, manual flying skills. Cognitive and psychomotor skills will degrade if they're not practiced. Automated systems are a tool for the pilot, not a replacement of us as operators or as monitors. And we need to consider the role of the automation in the overall system. We've been seeing way too many automation surprise and startle issues in recent years. We need to reverse that trend, and it's time to do that at the threshold of next gen. It's an opportunity. Thank you very much.
And thank you, Helena, for showing us the importance of defining and implementing proper automation policies and procedures in order to maintain our safe operations. We have now time for questions. We have the microphone set up on both sides of the room. If you want to make your way forward, we can ask our panelists some questions. And to begin, let me just start out, and I'll just ask this general to the panel immediately, is we've talked about as most of us are pilots in the room, is the pilot's role in this system and with all the complexity is, actually I'll let, we have one speaker there, I'll hold my question and, yes, sir.
All righty. Well, I appear to be the professional questioner, this question man of this affair.
Sure.
My question is addressed to Dr. Woods and the panel in general. And with regard to your discussion of brittleness and resilience in your model that you've created, what recommendations would you consider for a brittle, what is a brittle operational practice? And this is the setup for the operational practice. Our current expectation of pilots is that they will intervene during any or all malfunctions with the aircraft system through the use of manual flying skills. And basically that's keeping the shiny side up for 30 seconds to a minute while they figure out what went wrong. Most operators and many airspace areas require the pilot or aircraft to utilize all of the automation available from basically the time you get on the runway and apply takeoff thrust until pretty close to landing. There's little or no process or procedures provided for pilot maintenance of manual flying skills. And how would you model this, a solution to this particular situation that I think we find ourselves in?
So, I mean, very quickly, this is an old problem. I learned 30 years ago from some wonderful engineers, right, called bumpy transfer of control. We've talked about this in past incidents. It was part of the findings from the 1996 FAA Human Factors and Cockpit Automation report that I was privileged to work on with many others. And we pointed out that de-skilling and erosion of pilot skills would contribute to difficulties in this plan, this model of safety that you just described, that was was brittle, wasn't as effective as we thought, and it was going to become less effective because the automation works so well, pilots aren't learning about how to handle non-routine situations. The recommendation we made back in the middle 90s was you have to practice more non-routine situations. You have to practice handling a cascade of events. As you increase the autonomy, these are the kinds of trade-off slides we did for the Defense Science Board. As you increase this aspect of autonomy, there are predictable changes that will happen. Just like you can anticipate various conditions as you look at a flight plan and look at the weather and you know some of the risks involved in a particular route or a particular approach, we could see these, right? We still have not taken this seriously, right? We have new cases of problems in this area, and it's time we move forward. Now, notice the catch. The catch is it takes resources. It takes time with line pilots. We had the nice slide about the number of pilots and the cost of training. Oh my God, it's down to $30,000 each. Wait a minute. Doesn't that set off a light bulb?
Yeah, big.
Right? Right? This is what we said in the middle 90s, was that initial training to proficiency was getting easier and easier, but long-term growth of expertise, the new forms of airmanship that are necessary, were lagging behind. And you're not the only ones dealing with this problem. The military deals with this problem as they become more and more automated as well and have to manage these resources. Right? Now, we can talk about it, we can react to it, we can play whack an incident, or we can get proactive.
Thank you.
Thank you. Sean?
Yeah, this is kind of fun being a spectator rather than being up there. How do you like it? So,
We need to turn these lights down a
I'm
little.
enjoying it back here rather than up there. So this one is kind of directed kind of broadly towards probably the whole panel, but you know, Terry, you left your presentation on a little bit of a provocative note. We've interacted a couple times. I know we're out in Belgrade with the ADO group talking a little bit about recovery situations and what the appropriate use of aileron and rudder and from nose high and all these kind of different things. And that discussion kind of went towards, you know, beyond the procedures to an equipage question about, you know, the development of, you know, the so-called big red button, the recovery button. And that has obvious implications for UAS build-out. So I guess the question is that do you see, in terms of automation development and automation evolution, us ever getting to the point where there will be a fully automated recovery system integrated into these airplanes? Because if you take the case of the Qantas of the 380 accident, there would be no such system that could possibly have existed that would have saved that airplane. But for the, you know, very, very superb analysis and also triage that was performed on the part of the aircrew in basically dealing with something which the books, you know, clearly didn't speak to. It's, you know, Helena's that was the slide with the circle way on the outside of the ring. So kind of a, you know, pretty broad question, but I figured I'd throw it out to the panel because you guys look like you need some softballs thrown at you, maybe a little bit of a hardball. And I apologize ahead of time.
Thanks. A very good question and very thought-provoking. I think that from both the Airbus and the Boeing standpoint, what we're going to see in the future, in future designs, is even in degraded modes, either degraded hydraulics, or degraded electrics, degraded flight control modes, you're going to have some basic protections in the airplane that will keep you from exiting the flight envelope, the normal flight envelope. And I think you'll also find the ability to use the autopilot in a lot of degraded situations. You know, Mike alluded to that in his presentation earlier. And I know on the A380, which is a combination of a hydraulically controlled and an electro-hydrostatically controlled airplane, we can switch off 8 hydraulic pumps, because there are 2 per engine. We can switch off 8 hydraulic pumps and still fly the airplane normally on the electro-hydrostatic actuators and use the autopilot. So I think you're going to see that. As far as the other part of your question, which I thought was very interesting, whether you would have a recovery button where you could hit it and the airplane would automatically recover itself. It's a great concept, and when you think about it, let's think about it. But to actually flight test it and make it happen in the situations where you want it to happen, and then go to all the fringe cases, is very, very difficult. We have discussed, for example, a system where if you had a terrain encounter and the pilot was not properly reacting to a GPWS, would you have the autopilot come on and recover the airplane? And try to have the airplane itself avoid hitting the terrain. There again, think about all the fringe cases. What airspeed does it occur at? What descent rate does it occur at? What do you do about the thrust setting? Do you do that automatically as well? It's a very, very big matrix, but it is something that needs to be considered for the future.
You just made my case for resilience. Right? We can improve as we understand different kinds of problem areas. But the kinds of problems we face will continue to emerge. New variations will emerge as we get better at handling certain uncertainties and difficulties. Right? That's guaranteed. Actually, that's part of the complexity science results. You can't escape that in this universe. Maybe you've got a different universe we're going to start flying in. But in this one, we can't completely escape those trade-offs. And in the end, the ultimate safe haven is that you can demonstrate the ability to behave resiliently when these surprises happen and cascade. That's what you have to prove. Now, my responsibility to you is that I can come up with the measures and demonstrations of how to do that. Right? And that's my commitment to you, that the scientists will do that, and that we're trying to do that right now.
Yes.
Good morning. Dan Coogan with Delta Airlines. A question for the whole panel and even you, Dave. What we heard from our representatives was that maybe we can think of a piloting skills years ago as maybe it's a pyramid where the pilot was at the top of the pyramid and he kind of worked down through it. What I'm hearing today is maybe now it's more linear where the pilot is just a system that is on the line. But as Helena alluded to, there are maybe black swan events that suddenly the pilot has to perform in that higher level. We've also heard research where piloting skills are degraded. A lot of us in here have flown 727s non-automated. And if our skills are degrading, what skills will these new pilots who are learning in airplanes that sometimes are even more complex than the Airbus A320 that I'm flying, what kind of training or what kind of skills will they need, or what kind of tools will you present to them to help them with those events that are totally outside the realm of what the airplane can do?
Now, it's a fascinating question, as Dr. Woods pointed out, and these other things. So we try really hard at Boeing to have what we call transient free switches, and especially for normal operations. When you go from one command path to another command path, to have that transient between there not change state, okay? Our parking brake is one example. You have to have the brake pedals fully depressed to either set or release the parking brake. So therefore, you can't let the parking brake come off when the airplane's not stopped, and you can't put the parking brake on when it's not stopped. And we certainly try to have transient-free switches between modes of the airplane. It's one of the demonstration points. You roll the airplane, and we have a switch in the overhead that turns off the flight controls, and there's no bumps, there's no thumps, there's no nothing. But as we make the systems better and better and better, the failure mode, as we want to have amazingly reliable airplanes. We push off the transient until it's a more dramatic point. So we are now required, normally in your procedures, you write procedures for 10 to the minus fifth failures, right? And sometimes you write a few for 10 to the minus seventh failure, dual hydraulic system, right? We don't write procedures for 10 to the minus ninth failures because they're supposed to be designed out of the airplane. Richard DeCrispany in the A380 had a 10 to the minus 13th failure. That's why he calls it the black swan event. But as we push these things out, the experience goes down. I was giving a presentation one time at a Southeast Asian carrier, and part of my presentation was to talk about flying the airplane. I said, how many people, and I gave the same presentation at this airline down in Houston one time. And the 500 people in that airline meeting there in Houston, I asked them, how many people have ever spun an airplane? How many people in this room have actually spun an airplane, spun, 2 or 3 times? Right, great, I'd love to see that. I gave that same question to a Southeast Asian carrier, and not one hand went up. And I'm so daft, I thought, well, my God, I gotta change my presentation because my thing doesn't work. And I thought, no, change my presentation, heck with that. We have people who have never actually been in extremis in an airplane. But that's what we do in this business. And so as we go through these systems, it's very difficult as an airplane designer, because you want to push off, you want to have wonderful reliability and wonderful systems. But then when we give it back to the pilot, we're going to give them back a lot worse airplane than giving it back to them after a single fault. And I don't know what to do about that, honestly.
And I'll say one comment to Dan, and since you asked me also a little bit, is our manufacturers can build us awesome airframes that are safe and reliable. Our research community can provide us how we measure the brittleness and the resilience of our system, and we develop procedures and policies from our operators down to the pilots. But the key is who's sitting out here is you, the pilots. You are the ones that know what skills you need to practice, what you've maintained and what you haven't maintained, and what you need to practice to move forward safely. And that's the key, is that if the policies and procedures that we're getting do not allow us to do that, we need to be asking our companies to allow us that opportunity, or take the opportunities on the line to practice some of the skills, especially the ones that you don't use every day. So, okay, thank you. Paul?
Thanks.
Thanks. Just a quick comment, and thank you for an excellent presentation. I think the focus on the pilot-machine interface is good, but I would recall that that is a vacuum. No one in here today flies an airplane in a nice giant piece of airspace all by themselves. The coming changes to next-gen SASAR, the airspace, and the efficiencies that are being attempted to be designed into that airspace in order to increase the density of operations are going to force us, it seems to me, to rely on automation to the exclusion of allowing either a human pilot or a human controller to intervene. And isn't that the most brittle system you can imagine? Because here we're talking about manual flying skills, manual reversion, getting the pilot back in the loop. But if the pilot can't turn the airplane safely within the constraints of the airspace that he's operating in, it seems that we have a looming huge problem. And I wonder if anybody would care to comment on how exactly we're going to address that. Thank you.
Well, first of all, thanks, Paul, for that comment, because it is true that as the airspace becomes more and more dense, pilots have to be able to operate in that high-density environment, and they have to be able to do it with manual skill sets. I think that in our case at Airbus with our side stick controller, and with Boeing with their wheel controller, modern fly-by-wire flight control systems do compensate for a lot of the aerodynamic characteristics of the airplanes that the pilots never see anymore, because they're so well masked. And I think that the ability to control the airplane in terms of pitch and roll and bank, in the case of our airplanes, we have automatic trimming systems. In Boeing, the trim systems are very well designed, so with a minimum amount of effort, you can retrim the airplane to where you want it to be. To me, it suggests that in manual flight, we can meet those challenges in the future. But I think that that development has to be continued, and we also have to provide it on the training side so that pilots can see that they can, in fact, fly the airplane in those environments. And if they can't, if manual control is not possible, then other measures have to be taken if traffic becomes truly that dense in next gen.
The point that developing and designing autonomous systems as if there's no larger role to maintain resilience in the face of inevitable surprises and complications in real-world operations has been studied many times, and the answer is always the same. When you over-rely on the automation, it's going to be brittle. People will adapt. We can tell you exactly what will happen. Responsible people in some roles will adapt to make the system continue to work. We call that how the operator at the sharp end makes up for the holes in the designer's work. The designers get better and better, but right, they can have simplifications and limited resources as well. So the issue that you brought up is a systems design that's brittle. And this is the stuff that's covered in the Defense Science Board report for the DoD's ability to take advantage of autonomy. Now, I doubt there's too many people here who are pro-drone, but there are certainly audiences out there that are seeing drones as the remotely piloted vehicles, right? We don't call them UASs because in the Defense Science Board report we said it's way too much of an emphasis on the platforms. Just changing the title doesn't make it mean you're doing systems engineering properly. And we run through these factors in order to avoid the otherwise too low score on brittleness.
Helena,
Well, I agree very realistically. It's a looming problem, and I don't necessarily have a solution, but I do think that the training aspect of it, and now looking at our next generation of pilots, the millennials, they're going to have far less manual flying skills coming into our environment than anybody has in the past. So we do have to take our experience and mentor our younger generations. I think that's a huge part of it. As far as the overall, with facing a pilot shortage issue, I think we all have to take a huge responsibility in that moving forward. So
I guess I'd like to think that we could have the system, because Boeing also announced at Farnborough, I don't quite know where they got the data, but airplanes are running about 85% efficient. And most of it's in the operation that we're not using these key assets, these multi-million, $100 million assets to the greatest efficiency possible. And one way to do that is to take out all the slop and all the margin. Instead of having 4 miles on final, the requirement's 3, you put them at 3 miles. But that means that you don't get to fly at 150 knots because you want to that day, because you're not very comfortable flying at the assigned 140 knots, because that's the error differences that goes in there. But I'd like to think that we can devise a system and make an airplane that the pilots want to fly that flies the same guidance that the auto flight system would produce to the autopilot. If you're a 737 person, you know that the autopilot can actually fly. For the longest time, the autopilot could actually fly, it was a limitation of the auto flight system that kept down the navigation performance of the 737. The system was good enough, but the limitation was how fast the autopilot could react to the system. So I think there's a capability in the industry, and there's a desire in the industry to hand fly these systems. And then what I think of this is flying through the flight director. You know the airplane on the approach flies at 2 degrees angle of attack, or 2 degrees nose up. And if you're looking at the VASI, you're on speed. I don't care what you want to look at the airspeed indicator. If you're 2 degrees nose up in a Boeing airplane and you're coming down, the VASI lights are lined up there and they're not changing, you're on speed. Just the way it works. Across the board on an airplane. And takeoff is this and takeoff is that. I know at the Boeing company, internally at the company, we're having these conversations about what does an airplane do. Because remember, we fly the first flight on an airplane. Procedures that are developed for airplanes that have already gone through the delivery and build process. At Airbus too, also in Bombardier and Embraer, they fly the first flights on these airplanes, where procedures aren't actually valid yet, because the airplane's never flown. I mean, they are valid, right? But you don't know what the fault is in the airplane because it's never flown before. So I think there's a capability, and I think that's how you build resilience in the system, is you give the pilot the same capability as the automatic system does. And then you try to encourage the pilots to fly that manual system and understand what the airplane just did on the automatic system. So when the automatic system drops, they go, I've been here before. I've been on approach. I know the power settings. I know the pitch attitudes, not necessarily the power settings. I know how this airplane flies.
Thank you, Mike. We're out of time now for this panel, so I apologize, but we will take questions during the break after lunch. So I'd like to return it over to thank our distinguished panelists for coming, and then turn it over to Captain Hogan.